Section 4.2, there were tons of physics formulas. There were tons of physics formulas in section 4.1. But remember I said they would not be on a test. Remember I said that you would not have to memorize them. So I was seeing the initiative, the independence, the advanced academic capability of reading a book, and the textbook specifically, to find examples or watching watch-its to see how far you guys can get on your own, in trying to apply, basically, the idea that radians as an angle measure can be important in things like physics. So, I have your web assigned ready to go. Questions 1 through 18 are where we're looking. Anybody, where should I go first? Sasha?
4.
Number 4. Number 4 gives us the problem, estimate this to the nearest 1/2. What? Oh, I wish Ryan was here because he was the one that asked this last time. Kiddos, if we were to think about this as a circle, it says to the nearest 1/2 radian. If we were to think about this as a circle, okay, then you could draw this and be like, okay, oh, that's rough. Maybe I should not be using my mouse. Let me use, oh, I need a marker though. Okay. Here we go. If we were to mark this as a circle, that's a rough circle, but you guys know what I mean, right? If we were to mark this as a circle, at least roughly, what is a radian? Were you guys listening when Ryan asked me again on, today's Friday because yesterday was Thursday, I don't even know, was it Wednesday? When he asked me on Wednesday, what is a radian? What is a radian? Struggle bus, do I have to do it all over again? A measure of the what?
It's like the number of lengths around the circle.
But what length? But yes, it is the measure of the lengths around. But where do we get that from?
The radius.
The radius. Remember, I had the blue yarn, right? Ice. I had the blue yarn. None of us were able to answer radian for quite a while. I had the blue yarn. What did I do to it? I cut the diameter, then I folded it, I cut it in half, and what did I have? The radius. And then I started taking that blue yarn and saying, this is what? 1 radian. And then this is, then I tried to move it 2 radians, 3 radians, 4 radians, 5 radians, and then how many would there be if I had like a perfect measurement and I was doing it perfectly? 6.28, yada, 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 2 pi of those would, exactly, be the entire measure around the circle.
Oh, so it's like whatever number of radiuses completes the whole circle.
Technically radii, but yeah. And then I mentioned this whole, like, I could make a radius ruler, a blank ruler, and I could take my little radius, let's say that that ruler bends. If I took that radius for any circle, and if I made little tick marks, 1 radius, 2 radii, 3 radii, and wrapped that tape measure around whatever circle I was measuring, it would always be a ratio of 6.28 of those radii. So, think about it this way. Here's a radius, right? If I take this radius and if I wrap it around, what is this closest to? 1. This right here, starting in standard position, this is closest to 1 radius, right? So therefore, if I was to go to 1, or if I was to go to the nearest 1/2, 1/2 radius would be less if I was doing 1/2. So I could do the halves as like little green tick marks, so half a radius would be like this much, and if I was to wrap that around, it would be like right about there. So that'd be 1/2, and then 1 whole, and then 1.5, and then 2 whole, and then 2.5, and then 3 whole, and 3.14 would be all the way around. And then keep going all the way around, and you get to 6.28 if you could do this perfectly. So once again, what is this closest to? Just 1. What else? 1 through 18. I'm ready. 18. Says, find the area of the sector. Now you guys can access the Jamboard, so even if you didn't want to go looking in your notes, you just have to find which one talks about the area of a sector. There it is, and we have the formula for it. So, can you plug into a formula? Let's see. Can you plug into a formula? Let's see. So area of a sector, I need A equals, if I was to follow my formula on the Jamboard, A equals 1/2, let me double check, R squared theta. Let me double check. A is equal to, Jamboard, where are you, Jamboard? There you are. 1/2 R squared theta. Check. Hey, pause. What if it was all the way around the circle? What would my theta be if it was the whole circle? How many calzones make a whole circle? 2. So how many pi? 2 pi. 2 pi is the whole circle, right? So what if I plug in 2 pi for my theta? Doesn't the 2 reduce with the 1/2?
Yes.
And what do you have if you multiply 1/2 times 2 and that reduces and then pi r squared? If it was the whole circle, is this a formula you should recognize? Yep. Because the 2's would reduce and you would just have pi r squared, right guys? And that's exactly the area formula that we're used to using if it's the whole circle. So this would be for the whole area or the whole circle. It is pi r squared, but does it work with this formula? And the answer is yes. The answer is yes. Okay, so let's come back though. This is not the whole circle. This is only a portion of the circle. And specifically, what portion of the circle? Struggle bus. Nope. Pi is a calzone. Pi is a semicircle. This is 60 degrees. Yeah, but that doesn't help me. Because these physics formulas... Sorry, David, can you close that door? I can't anymore. Love them. It's Daddy. Thank you. I appreciate that. Guys, these physics formulas are based on using radians. Degrees, it will not understand. It has nothing to do with the circle measure at all. But radians, that has to do with like the ratios of the radii to the... Okay, so I can plug in. And so if I plug in 1/2, and then what's my R? 6 millimeters, and I do that squared. Come on, mental mathers. I have 36, and I have 36 over 6. Isn't that just 6 pi? Nice. And technically, I would be using the exact same units, which would be millimeters. If they wanted it to be something else, like centimeters or something else, which I don't have enough to even go to a different unit of measurement, but I could build a bridge, and I could do some dimensional analysis, but that's not what they're asking. Milliliters is good, so we just stop there. But in your Jamboards, I did make a point, and maybe you didn't write it down because it was the end of class, and you were like, whatever, I'll figure it out and look at the book, and then you might not have done that. All of these formulas are dependent on angles in radians. Degrees will not work in the actual relationships themselves. And there is no way to make degrees work, because once again, degrees are talking about how much of a whole circle's rotation you're moving every time you move a degree. Radians are actually related to the arc length, which all of these need. All of these, whether linear speed or angular speed or area of a sector, are all dependent in some way, shape, or form on arc length. Hence, the radians are necessary. Sasha, I'm guessing we got yours because you had the beginning and the end. Anybody else have questions to add in?
Oh, no, not
On 1 through 18.
Oh, yeah.
Yeah.
17.
17. But what's the formula? To find the angle, arc length and radius. So the arc length, how much is the measure? 24. What's the radius? 7. You guys just talked with me about how a radian is, right? Radians. Radians are how many radii. So how many 7s make 24? Well, 24 7s. Doesn't go in evenly. 21 would be 3. 28 would be 4. But then you guys could also actually take a formula. This doesn't need to be guessing. The formula says S arc length equals R radius times radian. So all we would have had to have done as far as like actually working this guy out would have just been to go ahead and say S arc length, which is 24, is equal to R, which is 7, times theta. You were just supposed to be finding the theta in terms of radians, which is what naturally happens out of this formula. So, check it. You see the division, right? Nice. Jackson.
So, I think I got it wrong because I gave turn it into a decimal, and is that wrong? Because
If it doesn't say round in WebAssign, it always wants the exact answer with no approximation. Does that make sense? It might say estimate, but it usually says round. And if it says round, it's okay to round a decimal. Otherwise, anything you put in that's not the exact answer with like a square root or with a fraction, it's going to be off. Yeah, good question though. Good question. Anything else? 1 through 18. My football guys, when are you leaving? Not until 11?
10:30.
10:30. Just keep an eye on the clock and you guys can head out when it's 10:30. Okie dokie. Ryan. Number 7. Co-terminal angles. Coming back to our notes really fast for co-terminal. Co, with or together. Terminal, ending side. I need the ending sides to be together. I need the ending sides to be at the exact same place. So coming back, we do technically have a formula that we could use that tells us to start at wherever we are, and then we can add multiples of 2 pi, technically add or subtract multiples of 2 pi, which means adding or subtracting multiple revolutions. Each of these, actually both of them, are talking about that we can add revolutions or we can subtract revolutions. We can add or we can subtract whole revolutions. Now, careful, it has to be an entire time around a circle. Add or subtract whole revolutions, which is why I need the 2 pi, which is why I need the 360 to get all the way around. Because if I'm at something like 30 degrees, to get back there, I need to add a whole revolution, which is why one coterminal will be 390 if you're doing degrees. Or if you're doing radians, if I'm at pi over 6, I need to add a whole 2 pi to get all the way back around to 13 pi over 6, which is one way. But you can also go the other direction, subtracting plus or minus multiples. I can also take pi over 6 and subtract 2 pi, which is 12 pi over 6, and 1 minus 12 is negative 11. That's just me reminding you guys of what was in the notes. Is there a question on the notes before I leave? Andy?
Yeah, I had a question. Yeah, what you were just explaining.
Okay.
So when you're subtracting or adding 2 pi.
To like your beginning angle, right?
Yes.
Good.
So, like, how would you like add it? I don't understand stuff. Because if you have
Plus.
like pi over 6, and then you're subtracting the 2 pi over 6, how would
No. Subtracting a whole 2 pi. Now, I could make that sixths, right? But if I cut 2 pi into 6, wouldn't there be 12 slices? I think of it in slices like a pizza. But 2 pi, if I'm cutting it into 6, 2 times 6 is 12. So I have 12 6 and 12 6, 1 pi over 6
So-
minus 12 pi over 6 is negative 11.
So you're just adding another times 6 over 6?
Well, I'm getting a common denominator.
Yeah.
But yeah. Yeah.
And then if you're adding it, like the one under the 2 pi
Uh-huh.
plus pi over 6,
What's 1 plus 12 pi over 6? So 2 pi is talking about 2 calzones, but they're uncut, if you want to think about it that way. Like if you want a visualization. 2 pi are 2 calzones. So 1 half circle, another half circle. So it's cut in half, but that's it. But if I'm talking about sixths, then each calzone needs to be cut into 6. Like that's kind of the easiest way for my brain to process. It might not be yours. If you're more mathematical, you could just be thinking to add a whole amount of pi with a fractional amount of pi. You can say 2 and 1/6, but that's awkward, especially with the pi. So instead we get a common denominator every single time.
so, like, let's just say you had like just 1 pi and then plus pi over 6, that would be 7 pi over 6?
Yeah.
Because you have like
6 over 6.
Okay.
Mm-hmm. And then what would be pi minus pi over 6? or negative pi over 6 plus pi? It would be negative 1 pi over 6 plus pi, though, which would be 6/6, which is why you would land at 5/6 pi. Now, the nice thing is unit circle totally has us doing this idea, or I think that one of the best ways that I visualize the unit circle is by using fractions. And so as we get into the unit circle, we're definitely going to be working on like where those angles come from, and not just like memorizing 7 pi over 6 is here, but realizing it's 6/6 plus 1. And that's the same reason that 4 pi over 3 is here, because it'd be 3/3 plus 1/3. And so seeing the unit circle, which I don't have yet because we're going to build it, but seeing the unit circle in terms of fractions so that we can actually land on these spots by having a visualization of how to get there, and not just like, well, if I don't have it memorized, oh well. But that's a coming. So don't worry, we're going to keep on working on those fractions. But for right now, for like the example that we were doing, I guess we weren't even to the problem yet. We were just on the examples from the notes. Yes, I was totally thinking about like taking these and like cutting it up, but also mathematically it's just getting a common denominator. Same idea. So let's take that idea on over here and say, okay, I can add or subtract multiples, even though I just did in the notes back here. I only had to do a multiple, like 1 adding of 2 pi to get to a positive, and 1 subtracting of 2 pi to get to a negative, but we can keep doing this all day long and just be spinning, 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 spinning. When do you land and have a coterminal angle? So let's see what's going on with this one. This one is a 2 pi over 3. So can you guys tell me what quadrant I'm in if it's 2 pi over 3? What quadrant am I in if it's 2 pi over 3? No, not quadrant 1. Because quadrant 1 has a half or less of a pi. Remember, pi is a calzone? Pretend it's a calzone, but it's not. I have a half, or a third, or a fourth, or a sixth. Remember, we start from over here. So that'd be like a sixth, or that would be like a fourth, or that would be like a third, or that would be like a half, right, of a calzone. But 2/3, isn't that past a half? Wouldn't that be over here? So check it. If you were cutting the calzone into thirds, it would be like this and this. And what's 2/3? Well, there's 1/3. Here's 2/3. What would 3/3 of a pi give us? That would be 1 whole half circle, right? That'd be 3/3. What would the one down here be? 4/3. What would the one down here be? 5/3. And how does that make sense as far as how many thirds would I have when I finish it? 6/3. And what is 6/3? 2 pi or tau. But 2/3 would land us right here in the second quadrant, just reminding you guys that quadrant 1 is that first one that we go through. Quadrant 2, as we rotate, is the second one. Quadrant 3 is the third one that we rotate through, and then quadrant 4 is the fourth one. But anyway, long story short, we're right here at 2 pi over 3. Now, as we're here at 2 pi over 3, question, how else could you land in that exact same, right, Ryan? Vocab word? Coterminal. How could we land on that exact same place? Another way, besides just turning directly to it. But we're not in degrees. So if you want to change this to degrees, you totally could. You could multiply by our conversion factor of 180 over pi. You could go to how many degrees this is, and then you could add 360. That is one way. But the other way, which I would prefer for you guys to work on, and it's going to be more helpful in the future, is to just say, hey, why not just go straight to adding, but instead of wanting to add 360, we add what? 2 pi, which didn't you guys just see that was 6 slices? So what happens if I add, and what happens if I subtract? What are they asking for? Radians, yes, so don't go to degrees, or if you do, come back. But it also says, give me 1 positive, 1 negative, one other way of turning there in a counterclockwise way, and another way of turning there in a clockwise way. Adding is like, well, we already added. We have to add a whole other revolution, hence the 2 pi plus. and it's going to be bigger than 6 pi over 3. The other way, I don't even have to go a full revolution, and I'll get there, but another way of looking at it is I have to backtrack on some of it that's been added, and then it's going to be a smaller angle remaining. Hey guys, what's 2 pi plus 6 pi, and they're both over 3? 2 pi plus 6 pi, both over 3? 8 pi over 3, that's going to be the positive one. And will I have a negative one by going the other direction? What's 2 pi minus 6 pi?
Negative 4 pi over 3.
Got him, coach. How we doing?
Good.
Ryan, how we doing?
So would the actual angles be 480 degrees and negative 30?
No, the actual angles are 8 pi over 3 and negative 4 pi over 3. You just don't like representing them that way. So the other way of talking about the angles in degree mode would be, let's see, 3 goes into 186 times, it'd be 8 60s, and 8 60s would be 480 degrees, would be another way of writing it. And then negative 240 would be another way of writing it.
So they're the right angle. I just need to,
You're at the right location, but you didn't come back to radians, which is what they were asking for.
I see you convert them to radians.
Yes.
So when you do
If you had 480 and negative 240, yes.
So why do you add 360 or subtract 360?
Because look at the little black arrow. That's your initial turning of like 30 or pi over 6. The initial turning is one way to land there. But if you've already turned this, if you need to get back to this spot and you keep turning in the positive way, you need one full revolution, so one full adding of 2 pi. And then, oh, I see. You guys were looking at the notes and I didn't actually write the 12. That's why it was confusing. I see, Andy, what you were looking at. What did I do? I think I added or subtracted the 2 pi, and then I meant to make it sixths. I didn't even look at the notes. I was just talking about the concept. But when I divide by 6, I need to also multiply by 6. So I forgot to multiply the 6 on top, which would have been the 12. And then 1 minus 12 is negative 11. I was looking up here where I was showing it what I thought was for the first time. Yeah, you're like, well, that doesn't make any sense. Why is it 11? Yeah, negative 11. But Ryan, if you're already here and you have to keep turning counterclockwise to get that positive angle. So another way of landing there is not just turning straight to it, but it's turning straight to it and going that full other revolution. That full other revolution, the only way to turn a full revolution is to add 2 pi in radians. Or go to degrees, add 360, come back from degrees, which is, I think, what your brain is doing. And then the other way to get an angle is from this positive rotation to subtract 2 pi. I have to get all the way back. And to get all the way back, I need to go a full revolution, either positively or negatively. If it's any partial revolution, then I'm going to land like somewhere else.
Here's what happens when you're drawing the arrow. It looks like you're just going in the same, you're just turning 360 degrees.
Which is equivalent to 2 pi.
And then you add 30 because
Do you have any Operation Christmas Child boxes?
Oh, thank you for asking, but no. I
Okay,
wish I
is
did.
it possible for you to hang this up somewhere? It's for Operation.
Do you want to get a piece of tape right there on the front table? You see it?
Mhm.
And then wherever you think kids would see it when you walked in the room. You could put it on the door. You could put it on like the cupboard, the blue cupboards in the back. You could tape it on there. Yeah, that looks perfect. Thanks, kiddo.
Alright, thank you.
Yeah. Ryan, remember, 360 is just how we talk about that angle in degrees. It's not how we talk about it in radians. In radians, we talk about 360 degrees as 2 pi. Right?
yes. Thank you.
Yeah, you're welcome. Paul, I'm looking to see, I need a key to get in the back. I figured out why your hand is raised. The dilemma is if I don't have that key, because it was a little crazy when I was running out of here the other day. The test is locked up, and so you'll have to take it from me next week. But I do have the key here. All right, last call on homework questions, because I believe we have both of those answers, and they're both on the screen. Those of you guys that went to degrees, Ryan, take a second and see if you can get, with converting, see if you can get an 8 pi over 3, see if you can get the negative 4 pi over 3. You want to convert real quick and make sure you can actually get that? And then Paul, when you're ready, it's going to be waiting over here on the desk. You can bring your pencil and your calculator. You go ahead and start that. Did it work, Ryan?
Yeah, I just gotta convert these.
Okay, so then last call on questions. 5, 4, 3, 2. David? I can show you the formulas. Then we can make sure they make sense, because the formulas for complement and supplement are pi over 2 take away something less than pi over 2, or pi take away something less than pi. If it's in radians, or 90 take away something less than 90, or 180 take away something less than 180. And so if we come here, if I do 1, which we already talked about as a radian, 1 as a radian for the top one would be right about here-ish, maybe a little bit lower. If 1 as a radian is right about there-ish, then it is less than 90. So all I need to do for my complement is pi over 2 take away. And then for my supplement, pi take away. Now these ones, since 1 isn't like a nice radian, it's not going to be a gorgeous answer, but that's also why they say to round. So if I just go to my calculator real fast and say, okay, if you want to think about geometry, your brain probably remembers 90 minus and 180 minus. So you just have to take that into radian form. And radian form would be like, all right, no big deal. Pi over 2, which is 90. Take away that 1 radian. And I have the first decimal, or pi, which is like 180. Take away that 1 radian. And that'll get me the other one. Now, why is the B impossible, though, for the complement? To have a complement, the angle can't go past, another way of saying it is can't be bigger than, right? Can't go past or can't be bigger than. Why isn't this working? I'm just going to get out of this real fast and get that over there. Oh, but now it's not going to work. Hold on. Give me 1 sec. There we go. To have a complement, it needs to be something less than, because I need to add up to it. And that was something we talked about last time. Remember that 2 radians takes these radii and wraps it around twice, which would put you in the second quadrant. So it's too big to have a complement because it's past 90. But it is small enough to have a supplement if I just do pi minus, and that would get you your decimal. Yeah. Michelle? All right, last question, guys. Number 12. So if you guys are ready, go ahead and get your notes open, section 4.2, and you might want to borrow a circular object because we're going to draw a unit circle. Number 12, right, kid?
Yeah.
Cool. Number 12 is exactly what Ryan was just mentioning a second ago, or kind of struggling with, that anytime we see a degree, it has a radian counterpart. Every time we have a degree, or see a degree, it has a radian counterpart, kids. So 45 degrees, there are a few different ways of looking at it. One way is if you remember that 45 is half of 90. For some people, it's easier. If 45 is half of 90, another way of looking at that is that it's 1/4 of a semicircle, because it takes 2 90s to be a whole semicircle, which I call, not just me, I'm just saying it, sorry, which I've been reminding you is pi. So one way of looking at it is 45 is half of 90, which means it's 1/4 of the whole half circle, which means it's 1/4 of pi. So some people would think of it that way. If you're more of a visual person, that might be helpful. So it's 1/4 of the half circle, it's 1/4 of pi. Another way, though, is that there are these conversion factors anytime we want to go from any, I just put a box if it's like it could change instead of putting a variable. If I have a degree, I can always do some dimensional analysis to get rid of degrees if I just multiply by what we call a conversion factor. Like 1 foot, 12 inches, things like that. But in this time, or in this case, I'm doing how many radians? It takes pi radians, 3.14 radians, to be equivalent to what a degree, in degrees, what would be 180. So what I'm doing is I'm multiplying by two expressions that mean the exact same angle measure, like this. And when I take any sort of degree and I multiply, check it, kid, there's a degree on top and a degree on bottom. My units reduce. The degrees are gone, and I'm left with whatever amount of pi is equivalent to whatever that angle is. And so 45 over 180, you could check it, but 45 times 2 is 90, times 3 is 135, times 4 is 180. We can reduce this to be 1 over 4. And also get pi over 4 by just multiplying straight across. So whichever one seems to make more sense. Both ways work. And that's exactly how you're going to do letter B as well. Just the angle is going to change a little bit. But negative 60. If you wanted to, once again, you could go ahead and draw that guy as, like if your brain does know where that is or where that would be. Then you could think of, well, how much of a semicircle would that be? Well, 60 is 1/3 of 180. 180 here is my guy over here, but this time I'm going in negative direction. So it'd be negative 180 or it'd be negative pi. So if you know that negative 60 is 1/3 of 180, you could just say, hey, that's negative pi over 3. But if you multiply by that nifty conversion factor again, like we did over here, it'd be the exact same one because you're going from degrees to radians. And so pointing you back to our notes real fast, and anybody else who also is struggling with looking at degrees and radians, we do have these conversion factors which can be really helpful if I just get rid of my annotating, get rid of that, get rid of that, get rid of this. Here it is. Anytime I need to convert, anytime I need to go from degrees to radians or vice versa, there are these conversion factors that we can multiply by that either obviously get rid of units like the degree mark, or not so obviously because they're not always written, but still get rid of radians. Is that okay? Cool. Let's go ahead and go into section 4.2. I can see us and I can hear us struggling with radians. David, whenever you're ready, if you can pop open the door. I think it's quiet again. But I hear us struggling with radians. And so we're going to work today on just trying to place radians in a circle. We're not going to go to section 4.3. Our goal is to finish up section 4.2. And as you guys, I'm going to pause the, thank you. As I pause the screen, you guys can go ahead and if you haven't yet, get a circular object drawn. Okay, before we actually start building the unit circle, I want you guys to remember what you know about a circle back from, oh man, chapter 1? What did we learn in chapter 1? What we learned in chapter 1 was the basic equation of a circle is x squared plus y squared is equal to, well, didn't we have x minus h squared plus y minus k squared equals 1 in chapter 1? But where's the h and where's the k, guys? Oh, it's centered at the origin, so it's 0, 0, no big deal. The coordinate pairs on the unit circle that you guys have a picture of, right? The coordinate pairs relate to trig ratios. By trig, what do I mean? Trig is short for what?
Trigonometry.
Okay, that's great, but this is an adjective. There you go. Trigonometric ratios. Coordinate points for angles relate to trigonometric ratios. So every time you're looking at your unit circle, if this is the way that you decide that you like to learn the trig ratios, our goal isn't necessarily for you to master the unit circle, but to know the trig ratios. So in all that we're doing, this is our main objective. In all that we're doing, this is our main objective. But one way of doing that is the unit circle. I'm going to show you multiple ways, but this is one way. Now, trig is referring to what? Why is it called trigonometry? Triangles. Where is the triangle in the circle I have tried to draw? Well, I've tried to draw it for you.
Right.
A triangle, a right triangle, can be drawn from any angle to the x-axis. Careful, not to the y-axis. Trigonometry. You guys caught it in the sense of try. Try, we're talking about a right triangle. So a right triangle can be drawn from any angle to the x-axis. Which means either from the angle down to the x-axis or the angle up to the x-axis. And that angle on the inside is seen as theta. Now, to be honest, some of these sections are going to go a little bit fast because you guys know some of these things, and I use geometry to kind of like get into the unit circle, whereas like the book actually says, let's just talk about the circle, and then let's just talk about the geometry, and then let's put it together. But I like showing you guys things like, hey, if I want sine of theta, or if I want cosine of theta, etc. Don't these have like triangle relationships, guys? So sine of theta, what do we know from SOHCAHTOA? What does sine equal in just a triangle in general? Oh no, SOHCAHTOA. What's so mean? Sine equals opposite over, careful, so is SOH. Opposite over hypotenuse. What would cosine be?
Adjacent over hypotenuse.
Okay, and I'm not going to go through all of the different, yeah, exactly. I'm not going to go through all of those right now. But the idea is, wait a minute, if sine is opposite over hypotenuse, guys, what is in the opposite, or what measures the opposite side in this triangle right now? It's not a number, but it's a variable. Which one measures the opposite side? Is x how far over or how far up you go to a y? X is how far over. Y is how far up. So wouldn't the sine be replaced with, or the opposite be replaced with a y? But what's the hypotenuse in a unit circle? Did anybody else notice what else is weird? X minus h squared plus y minus k squared. What was normally in the 1 spot for a circle? It wasn't 1.
Area?
No. Equation of a circle. X squared plus y squared equals what?
C squared.
Close. It wasn't a c though.
B
It was
squared.
it was for radius.
R squared.
So if there's a 1 in the r squared spot, question, what does it represent? What is the radius in a unit circle?
1.
It is the most basic circle with a radius of 1. So wait a minute. Y over 1, isn't that just y? And cosine would be x over 1, isn't that just x?
Mm-hmm.
So now all of a sudden we have this relationship of cosine being x, sine being y, and we can build all of our trigonometric ratios based thereupon, which is y, here we go, which is y or where this table comes from. All right, football guys, I'll see you later.
Bye.
This table says if you want a sine, now they went through and put t's instead of thetas. If you guys like the thetas better, you can totally use thetas instead. T is kind of being used in this first section because they're not totally going into all the geometry right now. We could put thetas all the way through, and if you want to do that, that's totally fine. So it's not sint or cost, it's sine of something, cosine of something, tangent of something, of an angle. But this table is saying, in those ordered pairs, if you're in a unit circle, the x is the cosine, and the y is the sine. And we can think about that for that entire unit circle. The x, for all of those ordered pairs, the x is the cosine coordinate, or sorry, the x coordinate is the cosine theta value, and the y coordinate is the sine theta value. So as a result, we can define sine to be y, cosine to be x, tangent, which is sine over cosine, to be y over x. Or if you want to think about it, SOHCAHTOA, if you want to, instead of memorizing those, draw a triangle. Cosine is x over 1, sine is y over 1. Tangent is SOHCAHTOA, opposite over adjacent, y over x. And then the other three come from there because cosecant says flip sine. There he is. Secant is defined to be flip cosine, and cotangent is defined to be flip tangent. Now those are kind of small, guys. Let me give you guys a second, because in some way, shape, or form, you do need to remind yourselves of the unit circle and where the trig is coming from. In a unit circle, there aren't triangles drawn. In a unit circle, there aren't triangles drawn. There are just angles drawn to a circle. So where does SOHCAHTOA come into play? Well, each of those ordered pairs could be seen as horizontal and vertical legs of a right triangle that correspond when the hypotenuse is 1, which it always is for any unit circle. 1 what? I don't know. It depends on how big you draw a unit circle. 1 inch, 1 foot, 1 mile, or just one arbitrary unit of the circle that you draw. I can see each of these ratios as the ways to get sine and cosine and tangent and cosecant and secant. And a quick heads up, if you look, secant and tangent, just in general, undefined. Undefined always happens when we have denominators equal to 0. These ones are going to be non-removable, so we're going to have vertical asymptotes at each of these places. What are the denominators of secant and tangent, both, according to our formulas? So when x equals 0, which x equals 0 on the y-axis, so here and here, secant and tangent are undefined at pi over 2 and 3 pi over 2. And cosecant and cotangent are at the y equals 0. So they're going to be undefined whenever I have an angle that lands on the x-axis, either at 0 or up high. Just a couple reminders of, on the actual axes themselves, the points are a little bit special. Remember, we have like 1, 0, negative 1, 0, because the unit circle is only 1 high or 1 wide. The axes are a little bit weird. This is more, I guess it works on the axes too. But the triangle idea is more for angles inside quadrants, like inside quadrant 1 or inside quadrant 2. On the axes themselves, you kind of just have to revert back to these formulas. The axes are weird, and on the axes, somebody can be undefined if it's like a division by 0. Ryan, you had a question a while ago. I'm sorry, bud. What's up?
Oh, I said, what is a T-set?
T could just be, they just make it an angle. They aren't quite relating it to geometry yet, so they're not quite going to Greek letters yet, but you can think of it as theta. They just use a T as an arbitrary, like physics time, they're kind of using that kind of variable. So it could be sine of x, cosine of x, but they don't want to put x because x's are like in the picture of the x coordinate. So then they could have used sine of theta, cosine of theta, but I think they were trying to stay away from geometry as much as possible and just show you the circle itself. I like showing it all together. Yeah. Are we okay? Do we have the page okay? So, oh, I need this to disappear. Hold on. Shoo. Thank you. Let's build our circle. As we build our circle. Now I know, I could just say, you have a picture on your phone, draw it. Right? I could. You have a picture on your phone, draw it. How do we draw it? Oh, all your nice cups that you love are on my back desk. Jackson can grab one, pass it around if anybody wants a cup. Anybody want a cup? To draw, to sketch, to trace? Go get one if you do. There's plenty. There's like 5 or 6 of them. You guys wanted the other day. Maybe just Jackson does. Wyatt wants one. Go grab one. The rest of you guys already have a circle-ish you're on. I want us to think in fractions. As you guys draw circles, I'm just going to play with fractions for a bit. So feel free, draw your circles. I'm going to play with fractions. Here are the ones I'm going to play with. I'm going to play with 30 degrees, 45 degrees, and 60 degrees. I'm just going to play. You might not know what I mean, but hold on. Oh, but wait a minute, hold on. Isn't that, those are the degree measures. Wait. I'm going to play with them now in terms of radians. 30 degrees is what fraction of 180, just as you guys are sketching? 30 to 180 is 1/6. And why am I comparing it to 180? Because 180 is a calzone is a pi. So 30 is like pi over 6, or a sixth of pi. 45 is 1/4. And 60 is 1/3. Now, if I was to think about 30s and 45s and 60s, and I was to count all the way around the circle, I could be thinking about pi over 6s and pi over 4s and pi over 3s. I'm just going to start counting just so we can see the different multiples. I could have 1 pi over 6. I could have 2 pi over 6. I could have 3 pi over 6. I could have 4 pi over 6. I could have 5 pi over 6. Or I could have 6 pi over 6. However, I'm going to take out 2 pi over 6, and take out 4 pi over 6, and take out 6 pi over 6. Why? Because 2 pi over 6 is the same thing as 1/3 pi. 4 pi over 6 is the same thing as 2/3 pi. 6 pi over 6 is the same thing as, well, pi, I mean, that's just halfway around. And that would have shown up in that very first sectioning of our unit circle where we had 0 and a half pi and a whole pi and 1 and a half pi and 2 pi. So as far as like the angles, if you remember, I'm not talking about the ones on the quadrants, I'm talking about the ones on the inside as far as like the idea of a triangle. The other ones can be defined by the order pairs on the outside. We'll get these in there in a second, but the only ones that are going to be inside, still with a sixth and not reduced to be a third, is 1 pi over 6. Oh wait, 3 pi over 6. Hold on, that's 1/2. That one should be gone too. 1/2 is going to be on an axis. So I have 1/6, 1/3, 1/2, 2/3, 5/6, and 6/6. Those would be all the different sixths. Then I could have 1/3, 2/3. I could do 3/3, but 3/3 is also at pi, so I don't need that one. And if I want fourths, I could have 1/4, which is in between a sixth and a third, because that's 1 and 2, a fourth's right in between. I'm going to have 2/4, 3/4, and 4/4, just counting by fractions. But 1/2 is already going to have, it's on the axis. 4/4 is already on an axis, it's pi. So if we were to count these around, now here's the bummer. I used to have lines in my old program. I don't think I have lines here. But if I was to label things, I could label things with 0 and pi over 2 and 1 whole pi and 1 1/2 pi, which would be 3 pi over 2. And I could come back and I could have 2 pi, but I've already made my way all the way around the circle, so I can just kind of stop there. If I was trying to put these guys in, though, and think about fractional pieces of pi. Well, hold on. If it's a unit circle, can't I just say this is over 1? Because I know that it's 1 big, like it's a radius of 1. I'm over 1, 1 comma 0. Guys, what would this point be if I'm just counting by ones? My x would be, no, my circle's only 1 big, whichever direction I go. So what would that point be? 0, 1, good. Over here, I'm going back 1, what would this point be? And then this point down here. Okay. Now, if I was to draw my 30s, if I was to draw my 30s, I want to think standard position. And we wrote earlier to the x-axis. Standard position to the x-axis, 30 up from the positive x-axis or 30 down, or 30 back from the negative x-axis, 30 down. These are all the little 30 degrees to the x-axis. What did we say would be the only ones between 0 and pi to be on the circle with a sixth underneath? These two, 1 pi over 6 and 5 pi over 6. So either adding 1/6 to 0 or subtracting 1/6 from 6 over 6. I didn't put my 5. Jackson, do you remember which one's going to be past this?
Oh. 6 over 6.
Close. That's at pi. And so I crossed that one off.
Oh, so 7 over 6?
Yeah, so 7 over 6. And if I keep going around, what would this one be? What would 2 pi be in sixths or in terms of
12.
sixths? That would be 12, so then go back one.
11 pi over
11 pi over 6. I want you guys to see how many of these other ones can you come up with. If I'm thinking about fourth pies, or if I'm thinking about third pies. How many can you label? If you're thinking about fourth pies, or if you're thinking about third pies, how many can you label? Chris. Yeah, go ahead. Thinking a very similar idea, but with fourths, thinking about thirds. Not with the order pairs, just with the angles themselves. If you're thinking about fourths, if you're thinking about thirds, I'm only going to show the top ones. You guys can see if you agree with those top ones. Ask me questions on the top ones. And see if you can fill in the bottom once you have the top. Maybe you're filling in the whole thing. Maybe you have it. You're still pondering. If we're just counting by fractions. because we didn't do section. How are we doing, guys? What do we think in the third quadrant? If we were counting by, let's do fourths. So 1/4, 2/4 would be a half. Remember, we crossed that guy out. 3/4. We're almost to a whole calzone. 4/4. We're all the way to pi, 4/4. What would the next one be? The next fourth. Huh? We could say 1 whole calzone and a fourth, but think improper fractions, like that guy. 1/4, 2/4, 3/4, 4/4, 5/4. Oops, wrong color. 5/4. What would be next? 6/4, which is 3/2. You see it? How about the next one? Which is also 8/4, take away 1. We're just counting by fractions, that's all. Michelle? Yeah. So let me give you a second, just in case you haven't filled in all the thirds. How do you try to get the thirds? Remember, once again, I could have just had you draw your unit circle at the very beginning of class. The question is, do you understand the movement? Do you understand the places of the radians? So many of you, if not all of you, are very unfamiliar with radians. You just want to take everything to degrees. They can be very, 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 very helpful, not for just this year, but beyond. To get more and more and more familiar with these radian guys. If I'm counting by thirds, 1/3, 2/3 is more than a half that passes over. 1/3, 2/3, 3/3. Got it. Where am I at now in the third quadrant? How many thirds? 4/3. Just keep counting. What's the next one? 4 plus 1 is? 4/3 plus 1/3 is? Which is also 1/3 less than 6/3, which is right back. So all of these guys that are on the axes, especially the axes, this can be seen as, depending on, it can be seen as 6 pi over 6. And that can be helpful for the 6. It can also be seen as 4 pi over 4. It can also be seen as 3 pi over 3. It can be whatever I want it to be, to help me get my references. My reference angles is what we call them, but we can talk about that more another time. I think that's in another section. If we were to move on, once we have all of our radians, let's go back to that very first quadrant again. Let's go back to that very first quadrant again. And not because we're trying to get angles. That was on the page before. We were trying to get angles with all of our different radians. Yes, we could talk about degrees, but my purpose is to make you more familiar with radians. And what if we were to talk about, ready, some very special numbers? This time, I'm not talking about the different radians. This time, I'm talking about ratios. In the entire unit circle, there are only 5 numbers. 0, 1, 2, 3, and technically 4. 5 numbers starting at 0, going to 4. But there are some special things about these numbers. First of all of them are being divided by 2. And second of all of them are being square rooted. You can get those patterns down. You have every single possible special number that shows up in your ordered pairs, except, hey guys, what's the square root of 0? And what's 0 divided by anything except for itself? That's just a 0. So we're not going to make it look all nasty and weird. We're just going to think of it as 0. And then what's the square root of 1? Square root of 2, I don't know. Not without rounding, and like Jackson said before, if you round, and anyway, it's best to keep it precise as much as possible. Square root of 3, similar, we're just going to keep it as a root 3. But, wait, square root of 4, what is that guy? And what's 2 over 2? These are my 5 special numbers in my unit circle. 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1. Now, some people, or like in calculus, for different reasons, sometimes we see this one as 1 over root 2. There is another way of looking at this. 1 over root 2 rationalized becomes 2 over root 2, but other than that, pretty much that's all we got. Now, well, I should say it this way. This is all we have for x's and y's, which remember are the same thing as sines and cosines. Don't just put sin, you got to put either like a t, Ryan, you were asking me that, sine of t, or I like going straight to geometry and thinking sine of theta and cosine of theta. But I want you guys not to think so much in terms of geometry and 30s and 45s and 60s, but just in terms of the smaller numbers all the way to the bigger numbers. So ready? We have the smallest to the biggest a ratio can be. The smallest one, x can be 0, the biggest x can be 1. The smallest y can be 0, the biggest x can be 1. Here we have the middle guy. And then we have the smaller, but not the smallest. And then we have the bigger, but not the biggest. Maybe this will help, maybe it won't. But for visual people, getting an understanding of the unit circle, this is one way of thinking about it. Now, at pi, no, sorry, pi's over here. At 0, x is the biggest it can possibly be. For every other point, x is, remember, careful, x is getting lower and lower and lower and lower. Technically not quite by equivalent pieces, it'd be more like, what is that? Okay, but there's the biggest x can be, and then x is going to go ahead and count down from there. So the biggest x can be, and then the bigger, but not the biggest, and then the middle, and then the smaller, but not the smallest, and then we have all the way down to 0. And we could label that all the way around the unit circle. And I can do the exact same thing for the y's, because the biggest y can be is 1. And then root 3 over 2, root 2 over 2, 1/2. And that's where all those ordered pairs come from. So can you guys take these numbers and can you label the xy pairs in your unit circle? You don't have to draw another circle if you don't want to. You can just keep on going and draw it outside the angles. Take those numbers, take those values, take those numbers and take those values. Fill in your ordered pairs. Now, we don't usually label our axes with these numbers because that makes it kind of messy. We usually just go straight to the order pairs. However, I guess we could if we wanted to. We don't normally label them, but we could if we wanted to. Yeah, I would just keep it on the same circle you guys have been building on.
Oh.
Go ahead and add in those coordinates. Add in those x's, add in those y's. I'm going to do the same. And if you finish your first quadrant, you should be able to keep going and label the rest of the unit circle because we have this beautiful symmetry. Maybe it's not beautiful to you, but we have this symmetry that just has us putting in negatives for x's or negatives for x's and y's or negatives for y's alone. If you just move those distances around the unit circle, you should be able to fill in the whole thing. again, there is geometry behind this. I could also explain them. But for right now, I'm just showing you the pattern of the numbers and then having you use what you know about x's and y's to move around the circle and fill in all your points. And you guys have a picture of the unit circle, or you had one, you can pull it back up and double check that you're writing it correctly. Using a phone as a ruler, genius. I love it. I might steal one. Go ahead and keep filling in that unit circle. And as you guys are filling in, what you should be seeing is that all of these x, y's, in the first quadrant, you should have gone a positive x and a positive y just because you know that's how you get there. You go right and you go up. In the second quadrant, you guys should be naturally just putting a negative for all those x's and keeping all those y's positive because you know how to move in an xy axis. In the third quadrant, you should be getting negative x's and negative y's because once again, you're going left, you're going down. In the fourth quadrant, you should be keeping those x's positives and making those y's negatives. Because these coordinates, these distances, these tick marks are exactly the tick marks all the way around. Could you be filling in from your picture? Yes. But should you also, once you've labeled your axes, just be able to move these distances over a little, over the smaller 1/2, up the bigger, root 3 over 2, over the middle, root 2 over 2, up the middle, root 2 over 2, over the bigger, root 3 over 2, up the smaller 1/2. You can move that way all the way around the unit circle. And once you have those written in, you can go back to your formulas. With things like a sine is going to be the y, and the cosine is going to be the x, and the tangent is like, hey, take the y over the x. Now that you have all those written down on your own and you have it in the picture, the question is now can you use those order pairs to fill in Sokotoa and Joshua? I just keep it in the Sokotoa order. It's usually easier for a few different reasons, even though I know it's y and then x and not x and then y. But it's my way of remembering it, and it's helpful for something that we call the cheater chart, which is like a shortened way of remembering some of this stuff. And then Choshuka. Just flips all the ones you already have. So if you guys can find your pi over 6, you've gone over the bigger, up the smaller. So the up is the y, the over is the x. And tangent says, let's flip them. Not flip them, sorry, put them over each other. And the cool thing is that the over 2's are able to just reduce mathematically. And we end up with 1 over root 3, which if you rationalize is the same thing as root 3 over 3, multiplying top and bottom by a square root. Cosecant says flip the sign. Remember, these are related. They all pair up. Cosecant says flip that guy. Cool. Flip this guy. Cool, except we got to rationalize, which would look a little bit fancier. And then this bottom one, we could flip this nasty version, or we could flip the version before it and just get root 3. And so we have some other special numbers coming out once we start doing like tangents and flipping. But still, our x's and y's will always be within those main 5 numbers. 5 pi over 4. This one's nice because I am going to use root 2 over 2's, but that's going to be past 4 over 4. That's in the 3rd quadrant, so I am going to have negatives, even though the numbers are easy because they're both the middle. Which makes tangent easy because they're over themselves, and when you ever divide something by itself, it's just going to be 1. But it does make cosecant and secant kind of messy when you go to flip it. It's possible, but it's messy. Because when you flip, let's see, what are you flipping? You're flipping negative root 2 over 2. You are going to have this denominator with the square root for both of these guys. Let me go ahead and show rationalizing. I haven't really shown it before. I've just kind of done it really fast. But rationalizing, remember, is multiplying top and bottom by a square root, which will end up getting you a 2 on top and a square root squared, a 2 on bottom. So you do actually end up with just a negative root 2 if you guys were to take as much time and as much work as you need, which is definitely preferable to the messy version. And then flipping 1, well, that's nice. An example of something in the 1st quadrant, something in the 3rd quadrant with negatives for everybody but the tangents and the cotangents. The 1st quadrant, everybody was positive. If we were to be on an axis, like at pi, my cosine, which is my x, goes negative 1. My sine, how far up or down? Well, you're not up and down at all. You're on the axis. That's a 0, but I did go left 1. Tangent, if I divide 0 by negative 1, 0 divided by anything is 0. But if I flip 0, I can't flip 0. It's undefined or a vertical asymptote for cosecant. I can flip negative 1 though. That's okay, but I can't flip 0. So you are going to have some undefined show up. And they might even ask you to go like a negative direction, which might have you find the location that is on your unit circle, but go there a different way because you go back negative pi over 3, which lands you here. At pi over 3, you go over the smaller, down the bigger. So you have that negative root 3 over 2, the positive 1/2. Whenever you do these divisions, it's nice because once again, those over 2's go away, they reduce. You start flipping things, which, yes, I know, in some ways are kind of messy. But as you practice your rationalizing, you'll remember how some of these patterns come about. Flipping 1/2 is like the best one ever. And flipping this one is a bit messy as well, unless you remember that root 3 and root 3 over 3 are kind of like the 2 different options for tangent and cotangent at these guys. But once again, some negatives, some positives. It all depends on what quadrant you're in, whether whatever you're doing uses x's or y's, and whether the x is positive or whether the y is positive, or if they both are or neither of them are. And that all comes back to, do you know how to move around a graph? Do you know how to make your way with x's and with y's to different locations? Do you know where to find the different angles as far as where they are in the different quadrants, etc.? All of these things will help solidify the idea to you. There are just a couple properties, and I think this is basically, yeah, we just kind of play with examples after that. So this is the last page of content, and I'll just see how you guys do as far as in homework. But the sign is always, if you guys notice, between negative 1 and 1. That's the highest it goes, but then it can also go that way in the negative direction. So sine is always in between negative 1 and 1, as is cosine. Other functions behave a little differently, but we're just talking kind of about the main 2, and then we build upon those for the rest. Every 2 pi, they totally repeat, even though they might have some other places of repeats in the unit circle as well. And then if they were to give us like a coterminal angle, the sines and cosines don't change because you're still in the same location. You're still in the same place with the same x's and the same y's. So to end off today, you guys just need to get down this even and odd trig function relationships. Who's even, who's odd, what that means. I'm just going to kind of play with it a little bit in a couple places in homework, but we'll look at why that's true in a future section. And that's it, guys. That's all I had for today. I'm going to go ahead and freeze the screen just to let you guys get down that last table.